Okay, so let's have a look at multiplying with exponents. So we're going to be using the modular operation here, and we're going to look at how we can efficiently create a value to the power of another value mod of a number. In cryptography, often a format that we use is that we take an exponent. So in this case, the exponent is e and d. So we take a value and we raise it to the power of the exponent. And then we take a mod n operation. So this is basically the RSA method here for dealing with the encryption key and the decryption key. The encryption key is e, n, and the decryption key is d, n. The e and the d work together so that the one reverses the other's operation. So in this case, we take the message, raise it to the power of e, and then take the mod of n. The mod of n is the remainder after the division. And because we deal with prime numbers, then magically we can actually perform mathematical operations without worrying that it's limited. The values are limited between 0 and n minus 1. So we end up with a cipher. We take the cipher, we raise it to the power of d, and take a mod n, and we magically get the message back again. The problem that we have is that we're going to get extremely large values. So this value here could be 2048 bits, the multiplication of two prime numbers, both 1024 bits. And then the operation here could be even larger than that, because the mod n is going to bring it in to make it smaller, so that we'll only have maybe 2048 bits now. But the multiplication here will be even larger than that. So how do we efficiently do that? We also see it in the Diffie-Hellman method. So with this, we agree a generator G and a prime number P. Alice generates a random number A, small a, passes G to the power of A. There's our exponent again, to the power of A, mod P. And Bob does the same, takes a value of G, raises it to the power of his random number P, and then they end up with the same shared key. Again, this value is going to get extremely large, and the problem is it's actually very difficult to crack that. Even though we know this value, and this value, it's very difficult to find what the value of A is. So it's quite a challenge to be able to do this operation. And basically the way that we typically do it is that we just keep multiplying. It's basically an add operation, but we do it many times to perform this power. Because here, c to the power of e is just m times m times m times m, and so on. So this is what our large numbers look like if they were displayed in an integer. So this is 2 to the power of 2024, which is a typical number that we would use for a value of n, where we take two prime numbers of 1000. So this should be 2048. Take two 1024-bit prime numbers and multiply them together. So this here shows you the size of the number that we get, 617 digits. So it's going to be extremely difficult to be able to multiply these extremely large numbers, especially that our processors are only dealing with about 64 bits at a time. So the operation that we have is that we can have an exponent, or to the power of a to the power of b mod p. But in Python there is also a pow, a to the power of b mod p. And then if we look at an example here, so this is an example using Python, just with the command line console. So it's 150,000 to the power of 200,000, and we'll take a prime number of 2 to the power of 256. Isn't a very large number, minus 1. Then we'll work out what the time it takes to calculate a to the power of b mod p. Then we'll do the same, but this time we'll use the pow a to the power of b to the p. So the two values that we get are the same. We can see here there's the result of this to the power of this, mod this. But the time it takes varies massively. So in this case it took 0.42 seconds to perform this operation. But if we use a more efficient method, which is power to the power of a mod p as a function here, we can see it takes a much less time. That's only about 1 millisecond. And the speed up is nearly 400 times. So this method here is 400 times faster than this one. And the reason for this is that Python here is performing the long operation of having to multiply each time through this addition, and then taking the mod of p. So we're going to get extremely large numbers. But this one here is optimized so that it knows the mod p operation and takes that into account. So one of the methods that we use for this is called the Montgomery modular multiplication method. And what it does is a fast way to factorize x times y, or x to the power of y mod n. Obviously x to the power of y mod n is a much more challenging operation than just x times y. So here's an example here, 10 to the power of 50, and we'll take an 80-bit modulus and generate a random number from here. This value must be odd for this method to work. When we multiply together, then obviously it's quite easy here, it's 500, but then when we take 10 to the power of 50 and then take a mod of this value, this is what we get as a result. So this is taking the Montgomery method, and this is taking x to the x double star y mod percent mod. So we'll just have a look at this and see how this works. Okay, so here's an example here. So we're using the Montgomery method here, the Montgomery reduction method. So we'll take 12 to the power of, let's see, 64, and we'll keep it quite simple. We'll just use 16 bits as a modulus, and you can see here's the n value that we have. So 2 to the power of 64 mod this value here gives us this value there. We can increase the value, so this is an 80-bit modulus, and we can see we still get the same result. Okay, so the code is here if you want to have a look at it, but it significantly reduces the amount of time that we take to create the multiplication or to do the exponent. Okay, so that's been an overview of exponents and how we can efficiently deal with them. Thank you.